I told you that z-scores were going to come in handy for a lot of things in statistics, and first stop is p-values. So p-values quantify the probability, probability, that's where the p-value comes from, that a given observation would occur by chance alone. For example, we saw earlier with our simulated 10,000 CS101 exam results that only 69 people attained a z-score above 2.5, and only 67 attained a z-score below -2.5. So if you were to randomly sample one of the 10,000 exam results from that CS101 exam, you would expect it to be outside of 2.5, that is, be plus or minus 2.5 standard deviations, only 1.36% of the time, right? Because we have 69 people above 2.5, 67 below 2.5. And so, if you sample just one test score from those 10,000, you'd expect it to be greater or less than 2.5 standard deviations, only 1.36% of the time. So equivalent to increasing our CS101 class size from 10,000 toward infinity, the probability of a score being further than 2.5 standard deviations from the mean of a normal distribution can be determined with the distribution's so-called cumulative distribution function, or CDF. So this CDF, the cumulative distribution function, means that we don't need to rely on calculating p-values kind of manually like this. We can use a built-in CDF method, which is in the norm module of the SciPy stats module. So if we pass in a z-score of -2.5, that gives us the probability, the p-value, on the low side of the distribution. So you'd expect, if we had an infinite number of students in that CS101 class, that you'd have 62 students falling below a -2.5 z-score. So the value that we got of 67 being below -2.5, that was because, remember, we sampled those 10,000 values from a distribution. So that was just a sample, but if we had an infinite number, an infinitely sized class, then we would expect exactly 62 out of 10,000 to be below -2.5 z-score. Let me plot this out to make a little bit more sense of it. We can see here that this is that p-value threshold of -2.5. And so this gives us our boundary at 2.5 standard deviations below the mean of the distribution. Now, if we want to also set a high benchmark for a very high score, like we've set a low benchmark here, we could do that by saying, okay, what is the p-value at 2.5 z-scores above the mean? So we put in positive 2.5 into our CDF method as opposed to -2.5. And so that gives us this p-value of 0.994. And we can use that similar to the way that we calculated p-value on the low end, that p-value on the high side corresponds to 0.0062 by subtracting this result, this p-value, by subtracting this number from 1. So what this tells us is, going back to our example of 10,000 students, we would expect, sampling from a perfect distribution, you'd expect 62 of the 10,000 to occur above a 2.5 z-score by chance, a 2.5 z-score by chance. In our sample of 10,000, we had 69, which is not far off, because this was, a somewhat random sample. So let's plot that out as well. All right, so now this is the equivalent high boundary on the right. So we had the low p-value boundary here. Now we've got this high boundary here. And so what this means is that the probability of having any scores outside 2.5 standard deviations below or above the mean is 0.01. So the probability from 10,000 students, you'd expect out of 10,000 students to have 124 values fall outside either 2.5 standard deviations below the mean or 2.5 standard deviations above the mean. And so let's plot those two thresholds out on the same plot. So what we're saying here is assuming a normal distribution, which we can often assume because of the central limit theorem, the probability, the p-value of a sampled value being at least 2.5 standard deviations away from the mean by chance alone is 0.01. So what I'm saying here is if you grabbed one random value from this entire distribution of 10,000 distributions, by chance alone, it's very unlikely that you'd sample someone from out here or someone from out here. Specifically, the odds of getting someone from down here or up here corresponds to a probability of 0.01. So about a 1% chance that if you sampled a value from this distribution, it would be such a low value or such a high value. So the convention in frequentist statistics is that if a p-value is less than 0.05, we say that it is a statistically significant observation. So we typically denote the significance threshold with alpha. So, alpha is equal to 0.05. And what this means is that if you sample a value from a distribution and the probability of getting that value is less than 0.05, there's a less than 5% chance of that, then we say that, hey, that is a statistically meaningful observation. It is unlikely to have happened by chance. Now, that 0.05 threshold is pretty arbitrary. It was devised a long time ago, and as I mentioned, when we have very large data sets, sometimes that threshold, that arbitrary threshold, falls down. But it's a reasonably good benchmark. We're saying that, only one time out of 20, only 5% of the time would we be making a mistake and saying that this is a statistically significant observation when in fact it isn't. It would just happen by chance one time in 20. So for example, to bring this idea of this alpha 0.05 statistically significant threshold to life with real numbers, let's talk about the probability of throwing coin tosses again. So if you were to do a 6 coin flip experiment, the probability of getting 6 heads or of getting 6 tails is 0.03. So you can go back to the coin flip probability method in the probability notebook that we were working through earlier in these live lessons, and you can prove to yourself using that method that the probability of getting 6 heads is 0.015 or 0.016, and the probability of getting 6 tails is also 0.016. So the probability of getting either 6 heads or 6 tails, we need to add together both of those probabilities. So 0.016 plus 0.016 gives us 0.03. So the probability of throwing 6 heads or 6 tails in a 6 coin flip experiment is 0.03. So if a friend of yours hands you a coin, your baseline assumption is presumably that it's a fair coin, that it's going to come up heads or tails on a given toss with a probability of 0.5. So that would be what we call your null hypothesis, that it's a fair coin. Then if you test the coin by flipping it 6 times, and it comes up heads on all 6 tosses, or it comes up tails on all 6 tosses. That observation should suggest that you reject the null hypothesis that it's a fair coin, because chance alone would allow such an observation less than 5% of the time, right? So if we get 6 heads in a row, or we get 6 tails in a row, the odds of either of those outcomes happening is 0.03 with a fair coin. So if you get that outcome, then you should say something's fishy here. The probability of that happening by chance is less than 0.05. And if you're a frequentist statistician, that is a magical threshold over which you say, that means that this is a statistically meaningful observation, and this coin is probably not fair. So if you'd like for any given distribution to be able to identify where this threshold is, where that alpha value of 0.05 is, the z-scores corresponding to that significance threshold level, that alpha of 0.05, can be obtained from a normal distribution's percent point function, or PPF. So this allows us to do the inverse of the CDF that we were using earlier up here. So PPF is the inverse. So with PPF, we can go from a p-value to a z-value, whereas CDF let us go from a z-value to a p-value. So to capture 95% of the values around the mean, you want to leave 2.5% of the values at the bottom and 2.5% at the top. That gives us that alpha of 0.05, 2.5 plus 2.5. So with a normal distribution, that threshold value of 0.025 at the bottom corresponds to a z-score of negative 1.96, and that 2.5 at the top corresponds to 1 minus 0.025, and that corresponds to a z-score of positive 1.96. So this means that at this traditionally upheld significance threshold of 0.05, a sampled value with a z-score less than negative 1.96 or greater than 1.96 would be considered statistically significant. So let's look at that on a chart here. We see that at that particular z-value of 1.96 standard deviations above or 1.96 standard deviations below the mean mu, these are the significance thresholds. So if you sample a value this low, way down here, or this high, way up here, a frequentist statistician would probably say, assuming that alpha of 0.05, that that particular data point is statistically meaningful, that it's not likely to come from this distribution. Nice, so I know that's a lot if you're being exposed to frequentist statistics and p-values for the first time, but I've got a couple exercises that we can work through together to help you understand exactly what's going on here.